got to read this thing because I haven't memorized it, so pardon my introduction here. Mike, standing here in the blue t-shirt, is, get out here and light so I can see what I'm doing. KF4EZ, Kilo Foxtrot 4 Echo Zulu, correct?
That's right.
All right. Mike developed a pretty early interest in ham radio from his father, W4GFG. His father was first licensed in 1948, and Mike was licensed first in 1969. So he's been at it for a while. Ham radio sparked an interest in antennas, which ended up leading to a PhD in electrical engineering. He spent 21 years at EMS Technologies in Norcross, developing airborne antennas for communications and radar. Astronomy has been another lifelong hobby, which includes eclipse chasing. One of Mike's crowning achievements was the design and construction of the radar antenna system used on the Mars lander that resulted in a successful landing. Mike's a pretty modest guy, but he's full of stories, and that's just one of them. He and his wife Beth, who's here, are both exceptional boaters, and that's where I met them. I've known them from my association with the Atlanta Sail and Power Squadrons. Atlanta is an America's Boating Club. The organization is a close partner with the Coast Guard and the Coast Guard Auxiliary in delivering the mission of recreational boating safety. As Mike and Beth have recently retired just this last year and split their time between Dawsonville and the west coast of Florida, we are very, very, very fortunate to have them as our guests tonight, presenting something completely different than what we normally have at our meetings. I trust that you all will be fascinated by what Mike's got to show us tonight. So with no further ado, Mike Goulet.
Thanks. All right, thanks very much. I really appreciate the opportunity to be able to share this information with you. The Great American Eclipse, so this, everybody knows about it now. August 21st, there's going to be an eclipse. It's going to go all the way across the entire country, and it's going to scrape across North Georgia, so we're very fortunate. This is an image of an eclipse as it's progressing, and just a couple of terms that we're going to talk about. And when the moon actually, when you look in the sky, of course, the stars and the sun, the moon and everything look like they're orbiting us because we're spinning, right? The Earth's spinning, so we see the stars go by. But the moon and the sun don't go at the same speed because the moon's orbiting the Earth as well. So the sun's going around because the Earth's turning, but the moon is also orbiting around the Earth, so the sun actually travels across the sky faster than the moon. So what happens is, in fact, about 12 degrees per day. So if you look at the moon, one day later, the moon will be 12 degrees further behind the sun. So the sun is going to catch up with the moon, and every time we have a new moon, basically the sun catches up with the moon and goes by it. But when we have an eclipse, the sun catches up with the moon and actually goes directly behind it. So that's what's happening here. And when the sun first comes along and touches the moon, that's called first contact. And then when the moon just gets behind the sun, entirely blocked, that's called second contact. And then third contact is when it first starts coming out again. And then fourth contact is when the sun goes on past the moon. So just to help motivate everybody to get up and go see this eclipse, my wife and I were really fortunate to go on an Atlantic crossing on a big sailboat in 2013, and we got to witness a solar eclipse out in the middle of the ocean. And the videotape is terrible because I was the one holding the camera, but I want you to listen to the audio because this is the crowd's reaction when the sun gets completely blocked. Sorry about the distortion. We haven't tried that before yet. But it's so impressive. It's incredibly impressive to see this event. So I'll talk a little bit about safety, the history of some of eclipses, the mechanics of the eclipse, and then we'll talk about the Great American Eclipse and what to look for. So the buzzword of the day, safety first, right? So when we look up at the sun, it's so intensely bright, we just have an instinct to look away from it because it's so intense. But it's not because it hurts, because you don't have any pain sensors in your retina. So when an eclipse is happening, a lot of people say, oh, the eclipse is much more dangerous than when the sun's out on a normal day. Not true. They're both just as dangerous. But when you're having an eclipse and the sun's blocked, it's not blaringly bright. And so you can look at it and it doesn't seem to be hurting you. But if you look at the sun when it's full out, you'll burn a big circle on your retina. If you look at the sun when it's partially covered by the moon, you'll just get a nice crescent burn in your retina. So either way, you don't want to stare at the sun without any kind of filters.
Save money on corrective.
So you have to be careful about what filter you get too. You can't just put on dark sunglasses, and you don't want to use smoked glass or pieces of film. Remember film? You want to actually get a proper filter, and filters you want to get a neutral density filter, which means it blocks all frequencies of the light. And for an eclipse, you have to have these really high rated filters. These are rated in kind of a logarithmic scale. So ND1 blocks, or lets 1/10 through. ND5 only lets 1/100,000 through. But most of the eclipse filters are up around ND6. So only a millionth of the light from the sun actually gets through the filter to your eye.
Are these equivalent of welding helmet filters?
You have to be careful, like welding, I think it's like 13 and 14 level is probably okay, but not all welding goggles are good enough. So you have to make sure you have, and don't use my numbers. I think it's 13 or 14 is kind of equivalent to these numbers. But so the best thing to do is go buy a cheap pair of glasses like these little $1.95, and they put solar filters in here. There's 3 different websites that have properly rated filters for viewing the sun. So they're CE rated, which is a European conformity regulation, or they're ISO rated with International, Standardization Organization.
Are these websites on the handout?
I think they are. Yeah. So then if you like fancy ones, you can get the Space Cowboy version here. This website's very interesting because you can buy the film. So for $25, you can get a square foot, and you can make your own glasses. In fact, when we were on the sailing trip, Beth and I made filters for our binoculars, and so we could view better. So anyway, that's...
There's an article in this month's Astronomy magazine that talks about making those things, and I think that's the place they recommend to go to get the material for it.
Yeah, they've been making this kind of stuff for a lot
The
of
smaller one is a spice cap.
years. Yep.
Huh.
The larger one, I think, was
A soup can.
a soup
Yeah.
can or a tuna can.
So we used these this metallized type filter. They used to sell 2 kinds, but I don't think they sell the metallized kind anymore. This is a little more risky because if you scratch them, it's just a very thin coating, and if you get a scratch, you can get the full sunlight through that scratch. Whereas the other kind of film that they're selling now, a scratch doesn't hurt because it goes all the way through. So a little bit about history. So eclipse comes from a Greek word, eclepsis, which means omission or abandonment. I'll talk about some myths and superstitions, some early predictions, and some discoveries that were made because of eclipses. So you can kind of imagine what it would have been like back when we had no real understanding of the physics of what the sun was and the moon was, and you have the sun is giving you life, the sun is providing you with food and heat, and all of a sudden, in the middle of the day, it starts getting eaten by the moon, right? So it was a very scary thing, and all the different peoples of the time came up with all these different explanations about what was happening. So the Greek side was these omens of disaster from angered gods. The Hindus thought this god Rahu, this deity Rahu, he was beheaded, and then his head flew off into the sky and ate the sun. That's what they did. And then all these different cultures had different demons, Vietnamese frogs, and South American jaguars, and even the American Indians. They had bears that ate the sun. In fact, that was their word for an eclipse. The sun got bit by a bear. these Indians, they would shoot flaming arrows to try to reignite the sun. On and on. The Arctic Indians thought it was a fight between siblings. There's even modern superstitions. Did you know it was dangerous for pregnant women? And it's also, if you cook food during an eclipse, it'll be poisonous.
Really? That's cool.
But it's not always bad, so if you plant flowers during an eclipse and they're bright. Sometimes things would happen in history that would actually reinforce these myths and superstitions. For example, in 1632, Muhammad's son died, right, coincident with an eclipse. So you can see how that would really reinforce this omen of disaster. And King Henry died just after an eclipse. You've probably heard about the lunar eclipse that saved Columbus' life and his crew. The crew was, their ships were eaten up by shipworms, and they had to abandon ship in Jamaica. And the Indians were keeping them alive. The Indians were the Arawak Indians, and they were feeding the crew and giving them water. And after a time period went by, after several conflicts between Columbus' men and the Indians, they just said, we're not going to do this anymore. They stopped feeding them. But Columbus checked his almanac, and he said, there's going to be a lunar eclipse. So he set up a meeting with the Arawak chief, and he said, in 3 days, my Christian God is very angry at you people for not helping us, and he's going to turn the sun blood red. And of course it happened, and it scared the hell out of them. And they started feeding them again. True story. And then everybody knows it took a lunar eclipse in 2004 for the Red Sox to win the World Series after 85 years. And they've done it a couple times since then, but it took that eclipse to do it the first time. Eclipse is the first known predicted eclipse. It's 585 BC, a long time ago. And supposedly this eclipse occurred during this battle between the Lydians and the Medes, and supposedly it ended the war. But that may or may not be true. It looks like there was an eclipse in 585 BC, but it looks like the path of the eclipse probably wasn't close enough to this battle to really have caused that. But the Chinese and the Babylonians were well known for recording astronomical information. All the way back, 2800 BC, they had their astronomers, and every night they would record what was happening in the sky. And when one astronomer died, another one would take over. So they had generations and generations and generations of history of what was happening, and they started recognizing patterns. And the Babylonians recognized this pattern of solar eclipses that were similar, and that's called the Saros cycle. We'll talk more about the Saros cycle. It's 18 years, 11.3 days long. And many scientific discoveries have taken advantage of eclipses. Aristotle, way back in 384 to 322 BC, he used a lunar eclipse to show that the Earth was round. 2,000 years before Columbus, he knew the Earth was round because of the curvature of the shadow that was falling on the moon from the Earth. Hipparchus, he used a solar eclipse to compute the distance to the moon. He was only 11% off, not too bad. He also used lunar eclipses to determine longitude. Longitude is really difficult to determine if you don't have a very accurate chronometer. You need a very accurate clock so that in two different places you can look at the positions of astronomical objects, and you have to know the exact time that has gone by to figure out your longitude. Well, an eclipse, a lunar eclipse, happens at the same place on Earth at the same time, everywhere. So two people could be at two different places recording the angles to certain stars, go back and compare notes, and they could figure out how far they were in longitude from each other. They actually, Lewis and Clark used that as well. Edmund Halley, he was the first to accurately predict an eclipse within 18 miles and within 4 minutes of it happening. And in 1715, that would have been a very difficult thing to do. Francis Bailey, if you've heard of Bailey beads, and these are Bailey's beads, he described what causes those, and we'll talk about that. Helium was discovered during an eclipse on the sun, 24 years before it was ever discovered on Earth, because they were using spectroscopy during the eclipse and looking at the light and looking at the frequencies of light, and there were no elements to explain the frequency pattern that they were seeing. So they called the element helium for the sun. And then one of the most famous discoveries was the validation of Einstein's general theory of relativity. Because Einstein said that that gravity will even bend light. And so they said, well, if we look at a star and the light's going to pass really close to the sun, then it should bend, right? Problem is you can't see stars when they're really close to the sun because the sun's so bright. So if you wait till you have a total solar eclipse, then you can look at the position of this star and compare it to where it should have been based on when the sun wasn't there. The problem is that the change in position is like a 10,000th of a degree. So they had to do this very, very careful measurement. And what they found was Einstein was right. The star wasn't where it was supposed to be. The star looked like it was here when it should have been right here. But because the light bent, your eyeball pictured it as being up here. So some of the mechanics of the eclipse, and there's different kinds of solar eclipses. The eclipse we're going to have is a total eclipse. You can also have annular eclipses, partial eclipses, hybrid eclipses. How do you predict these things, and some statistics. So everybody knows what we're seeing is the shadow of the moon. The sun's light gets blocked by the moon and causes a shadow on the earth. But to look at the type of shadow that is created, let's think of the sun as the sun has physical extent, right? When you look at it in the sky, it's about a ½ degree across. So you can think of it as a bunch of light sources in a line, and each one of these light sources is casting a shadow through the moon.
Cool.
So if all of these little sources are blocked, and that only happens right in the middle, then you get a very dark shadow. And if like this source here is going to be visible on this side of the Earth, right here, but not on this side of the Earth, so you get a partial shadow, and the shadow is not as dark. The dark part of the shadow is called the umbra, and then the lighter part of the shadow is called the penumbra. The umbra has to get all the way down to the Earth to have a total eclipse, and that's what's going to happen here in August. The umbra shadow has to get all the way down to the Earth. But that doesn't always happen. The main reason it doesn't is because the moon's in an elliptical orbit. So when the moon's at perigee, it's closest to Earth and it looks bigger in the sky than when it's at apogee. So this is the difference in the size of the moon between apogee, the small moon, and perigee, the big moon. So you can see why in some cases the moon's big enough to block the sun, in some cases it's not. This would be an annular solar eclipse. The umbra doesn't quite get down to the surface of the Earth. So no matter where you are on the Earth, you're always going to see some of the sun's surface. And that's, when you're directly below, this is what you see. Sometimes it's called the ring of fire. Really neat event, but nothing like a total solar eclipse. A total solar eclipse blows this away. Here's an eclipse on Mars. This was taken by the Mars rover. They can't ever have total solar eclipses on Mars. The moon is too small. Or the moons of Mars are both too small. But they still pass in front of the sun, and they still cause these annular eclipses.
Question.
Yeah, sure.
Why doesn't the moon look round from that angle?
It's not. Mars's moons are so small that they're not big enough to form into a sphere. And there's also what's called a hybrid eclipse. It starts out as an annular eclipse because the umbra doesn't quite get to the Earth, and then later it gets to the Earth, and then the reason is because the Earth is spherical. So if you see the eclipse early in the morning, so I'm looking off the edge of the Earth here towards the sun, I'm further away from the moon, so the moon looks a little bit smaller. And then if you see the eclipse at high noon, then you're closer to the moon. So the moon actually looks bigger when it's directly over your head. It measures bigger directly over your head than if it's over on the horizon. Even though on the horizon it looks big, but that's an optical illusion. So it seems like, the moon goes around every 30 days or so, right? It seems like you ought to have an eclipse every 30 days, but that's not what happens because the moon's orbit is tilted relative to the Earth's orbit. So the Earth orbits around the sun on this line called the ecliptic, and the ecliptic then forms a plane. And the moon's orbit is tilted 5 degrees to the ecliptic plane, and so it only crosses the ecliptic plane in these two red spots. Those are called nodes. So you can only have an eclipse if the moon is actually in the ecliptic plane. Otherwise, it'll be above or below the ecliptic and won't block the sun. So several things have to happen. You have to have a new moon, because new moon happens when the moon's towards the sun. And you have to have this nodal alignment towards the sun. So if you go 3 months later, and Earth's over here, you can see when you come to the moon's going to be below the ecliptic and won't block the sun. 6 months from there, the moon's going to be above the ecliptic. So it looks like what you should have is, oops, back up, going the wrong way. You should have an eclipse here and then another eclipse 6 months later. Well, it turns out that's about what we have. We have roughly not total eclipses. We have 2 solar eclipses roughly per year. Sometimes more, because sometimes these nodes are close enough to cause an eclipse, and then 1 month later you get another eclipse. Sometimes you can have 2 eclipses 1 month apart, and then 6 months later you can have 1 or 2 more. So the most you can have is technically 5, but typically you can have 2 to 4 eclipses per year, solar eclipses. So the Saros cycle thing we talked about, the Babylonians discovered this pattern, and it's a pattern between similar eclipses. And a whole bunch of things have to happen at the same time to have a similar eclipse. First, you have to have a new moon, right? Well, that happens every, let's be real accurate here, 29.531 days. Every 29.531 days you have a new moon. But the moon's only at perigee every 27.555 days. And then the time between the nodal alignments is approximately 6 months. Not exactly, because that ecliptic plane is also orbiting. It's very complicated math that has to be done. But all these things have to happen at the same time. So you kind of have to find the least common denominator of all these things. And that happens to be 6,585 days. It takes 223 new moons, 239 perigees, and 38 nodal alignments to get to this 18-year, 11-day, 8-hour similar eclipse. And that's a Saros cycle. But they're similar eclipses, but because of the 8 hours, the next Saros cycle eclipse won't happen on the same place on the Earth, because the Earth will have turned 8 hours. So you have to have 3 Saros cycles to have the same eclipse in the same place. That's called an I can't ever say a word. I need to have a drink to say that word. Exoligmos, as I say. 54 years and 34 days exactly. So in every 3 Saros cycles, you have a similar eclipse in the same place. In these eclipses, there's actually 40 Saros cycles running simultaneously at any given time. And they spiral across the planet. They start at the top, they start up in the Arctic, and they work their way around for 1,300 years, and then they fall off the planet. So here's the Saros cycle that we're going to see is Saros cycle number 145, and this is actually the first total eclipse for Saros cycle 145. It's the 17th eclipse for this Saros cycle, but it's the first total one. They were all partial before this, and that happened in 1927. And then every Saros cycle, they just up the member number. So it's a Saros cycle 145, member 17. Here's member 18, 19, 20, 21. And notice how they come across 8 hours apart, and they spiral down the planet. And eventually they end up falling off the southern part. So in 2648, if you want to go to Antarctica, and it'll probably be warmer then because of global warming.
Or a t-shirt.
But if you come back up here, back to our time. Okay, so here's our eclipse, 2017. So three Saros cycles before this, 1, 2, 3. So we had another eclipse, very much like that one. It was just up in Canada in 1963. 1, 2, 3. This is our eclipse. 1, 2, 3, and then there's going to be one just south of us going through the Mexico.
There's one that was visible in this area.
In 1970?
I was
I think
thinking in late 80s.
That was a annular eclipse.
Okay. Okay.
There was a total eclipse that hit Georgia in 1970, I think it was 70.
Okay.
But we haven't had one, a good total eclipse for a long time. So based on a lot of history, 5,000 years of eclipses, 12,000 eclipses, we have 2.38 per year. 1.58 of them are total. And the chances of having a total eclipse in the same place is 1 in 374 years. So we're really lucky to have this eclipse coming through Georgia. And sometimes they come in bad places where we don't really want to travel to go see them. But we're actually super lucky in Georgia because this 1 in 374 year chance is we just blew that away because we had one in 1970, 2017, 2024 there's going to be one that touches Kentucky and then another one clips Georgia in 2045. So we have a whole bunch of total eclipses happening well within this time period. Of course, somebody may have seen this one. I missed this one, but don't miss the 2017 one. If you, another reason not to miss this eclipse is because the sun is actually growing a little bit every year, and the moon's getting a little bit further away from the Earth every year, getting smaller and smaller. So in 600 million years, we won't have total eclipses anymore. So you need to make sure.
Write that down.
NASA has some really neat animations online. This is an animation of this eclipse. So this is the penumbra shadow started, and the penumbra shadow covers the whole entire continent. That means the whole continent is going to see a partial eclipse. At least part of the sun's going to get blocked by the sun. So as we rest this thing on, there's the total. The total eclipse diameter is 70 miles or so. You have to be within that 70-mile swath to get a total eclipse. So it starts in Oregon, and it travels all the way across the whole country and leaves the country in Charleston, South Carolina. Notice the shadow's elongated when the eclipse is happening in the morning, and then it's elongated again when it happens in the afternoon. But right around where we are, it's going to happen pretty close to noon, and so we're going to get the moon will be the biggest because it's up high, and we'll get the longest eclipse. The eclipse lasts in our area like 2 minutes and 40 seconds, something like that.
Do we know what time? Well, we should know.
We know exactly what time it's going to be. So here it shows the how much of the sun's blocked. So 25%, 50%, 90%, so forth. As you move across the continent.
It's a good part of the day.
Yeah.
We'll see some darkening from it.
Oh yeah,
Just
sure.
from-
Well, you won't see the darkening, but you won't perceive that until it starts getting really close. But
Right.
with a pinhole camera or with your good filters, you can look right at the sun and you can see
That's
it
it.
starting to take a bite out of it. I think it lasts about 3 hours, I think. From first contact to fourth contact.
Okay.
Here's another neat simulation where the moon's eye view, they called it. So you can see as the moon moves, as the sun goes across behind the moon. So the sun's out here moving across. The sun's of course moving to the west, but the shadow races from west to east because you can see how the shadow would occur because of where the moon is. Oops. So start over again. So here's where the eclipse first hits in Oregon, goes whipping across the country as the sun moves over. And NASA has a bunch of other neat simulations. Here's a picture of an eclipse from space. So that's what the umbra shadow looks like from a satellite. So if we're online, sometimes this site takes a while to get into. It's being used heavily. It's really a really cool site. You need to check this out, and it's on the list. So go up here and go to the instructions and see all the features that this map has before you play with it. But it's just like a Google map, so you can anywhere you put the cursor, you can zoom in. If I want to zoom in on North Dakota or whatever, and you can move the map back and forth. So if I go over here, So this is the eclipse first starts out in the Pacific Ocean. These yellow lines are 10 minutes apart. So this shadow is really moving. This, when it first starts, the shadow is moving like 6,000 miles an hour across the Pacific. When it gets over to us, okay, here's the shadow. It's moving something like 1,200 miles an hour between these 10-minute tick marks. So these two points here are important because right in southern Illinois, you can't probably read that, but it says GD, which means greatest duration. So that's the longest eclipse that's going to occur right here. And if you hover over that mark, it'll show you the latitude and longitude. It tells you the duration of the eclipse, 2 minutes, 40.2 seconds. And down here it tells you first contact, the exact date, time, altitude, and azimuth position of the sun. So this one is 1652, this is universal time, 1652, and then the total eclipse starts at 1820. So 620 universal, this is central time zone, that's 5 hours for daylight time. So that would be
120.
Yeah, 120, 1320. This other little symbol here is the greatest eclipse. It just means that the moon is going to be the biggest at that point. The time difference is nothing. It's 1/10 of a second difference here and here. The other thing that's really cool about this map is you can click anywhere on the map and it'll tell you what's going to happen right there. So out here, of course, it's not a total eclipse. It says here partial solar eclipse, 97% coverage, when it starts, when it stops. If you're out right at this, anywhere between these two blue lines, you will get a total eclipse. But the time will get less and less as you get close to the line. Like out here, it's 1 minute, 19 seconds. So it still hasn't, it's kind of amazing. It's 2 minutes, 40 seconds here. It's still 1 minute, 19 seconds there. But if I just go beyond the line, it's zero. It's not a total eclipse anymore. So if you're going to be somewhere near the line, be very careful. Don't make sure you're 20 miles inside the line so you get a good total eclipse. And if you come down here to North Georgia, you can see, so anywhere up here in the corner of Georgia is right in the middle of the path. But don't hang out right at the edge of the path. Go ahead and drive a few miles and get right under the path of the eclipse.
Where are you guys going to be?
We have relatives in southern Illinois, so we're going to be right up here by the.
Okay.
And mainly, so the reason I'm going to be up there is coming up on the next slide. But if we come down to Georgia,
Show them Lake Murray.
Lake Murray is over here.
The Atlanta Power Squadron is doing a trip to Lake Murray, and so we're going to be out on a boat on Lake Murray and you can see it's right on the center line.
So right in the middle of Lake Murray, it's 2 minutes, 34 seconds duration. So play with that map. That's a pretty neat tool. So here's the problem. We're in a very rainy part of the country. It's fortunate because August is the least cloudy time in this part of the country, but it's also still a 50-50 proposition that you have clouds or no clouds. So one reason we want to be up here, it's a little bit drier, but also we're going to look at the weather the day before and decide which way we're driving. So that's the problem with being stuck on Lake Murray. Is if you have clouds for 2 minutes, you miss it.
You're stuck.
But you can see another one in, what, 300?
Yeah, you can wait
374 years.
So there's all kinds of neat things that happen during the total eclipse. Shadows get sharper, these pinhole camera effects, shadow bands, Bailey's bead, Simon ring. You can sometimes see the chromosphere, and we'll talk about that a little bit, the corona. Birds and animals think it's night, so they just go into night mode. You feel the temperature drop, the bright stars come out. So to understand some of these features, we need to understand just a little bit about the sun. The photosphere, this layer of the sun, is what's brilliant white that you can't look at. And that blocks your possibility of seeing any other part of the sun. The chromosphere is actually outside the photosphere, but you can't see it because it's not bright. It's orangey, reddish color, but it's not intensely bright. Remember, the sun is just a gas ball. There's no defined surface. And so the light from the photosphere goes right through the chromosphere and blinds you, and you can't see the chromosphere, except during a total eclipse, since the chromosphere is outside the photosphere, it can block the photosphere, and at that instant you can start seeing the chromosphere, which is red, and you can see flares coming off the sun and things like that. And then further out is the corona. So the corona is the far out atmosphere around the sun, or the gases that are being ejected from the sun at high velocity, and that spreads way out beyond the sun. So that becomes visible only during a total eclipse. There's no other time you can see the corona.
And that's the layer that affects ham radio,
That's,
correct?
It's all solar material coming
Okay.
off the sun that when it gets here, it ionizes our atmosphere. It's interesting that the temperatures are so different. The photosphere, which is the brilliant bright, is 5,000 degrees, but the chromosphere is much hotter, and the corona is 1.5 million degrees. And the you got to be careful about temperature because the density is very thin out here. So the temperature, it looks like the temperature would have to get hotter and hotter as you go towards the source of the heat, but that's not true because it's a function of how much heat there is. And if there's no material there, it can be very hot, but if you only encounter a hot particle every so often, there's not that much heat content. Now, you don't want to be there in the corona. But in Earth's atmosphere, even in Earth's atmosphere, if you go up to the level where the satellites are orbiting, the temperature is very hot. The particles that are there aren't very many particles there, but they're hot. Here's another view of the solar surface. So the photosphere is a nice uniform thin layer. That's this white layer. The chromosphere is very jagged. It has these spicules, and that's the red layer that you can see when the photosphere gets blocked. And then the corona goes way out beyond even the diameter of the Earth. This is the diameter of the Earth relative to those layers. So the shadows get very sharp during this total eclipse. And so do you know why stars twinkle?
Atmosphere.
So it's the atmosphere, right? Because you have a pinpoint of light, and the atmosphere causes the light coming from that star to refract around and bounce around, and you end up seeing light from two different directions, and they add and subtract. So that you have constructive interference and destructive interference. And so the star gets bright and dim and bright and dim. Similar thing happens when the sun gets blocked by the moon. When the sun becomes a very thin sliver, then in that direction, you get the same effect. And so what happens is you get these light and dark bands. This is an artist's rendition, but this is actually a guy trying to photograph shadow bands. They're very hard to photograph. So that's destructive and constructive interference from the very thin light coming from the sun. It's easier to see than it is to photograph because your eye picks up the motion, and the wind is moving the atmosphere so that the shadow bands move across the ground. So people lay out these white sheets on the ground and try to find shadow bands. The reason that your shadows get very sharp is because we have umbras and penumbras too. The sun has an extent, so some of the sunlight, is partially blocked and some's totally blocked. Yeah, it's a lot different than the moon. The moon has a giant penumbra and a little tiny umbra. We have a giant umbra and a little tiny penumbra because of the distances. So our shadows look blurry because the edges of our shadows have some light squeaking around the edge. When the sun gets real thin, that little penumbra layer gets thinner and thinner and thinner, and the shadows get really sharp, and that's what they're showing here. And everybody probably made a pinhole camera when they were a kid. This is a real fancy one where you can actually block all the light, stick your head up inside. You need to make, the pinhole needs to be real small, so what they do is cut a fairly big hole in the cardboard and then take some tin foil and just poke a tiny hole in the tin foil. And then you can project the sun onto a white sheet. You can also just do it with 2 cards and just stand there and do it like that. But the pinhole effects happen all over the place outside without even building a pinhole camera. So this is light squeaking between leaves in a tree, And each one of those little cracks of light between the leaves is a pinhole camera creating an image of the crescent sun. And then here's somebody doing it with some little kitchen tool, and the guy's making little crescent suns with his fingers. That happens every day. We don't even notice it. I actually went out this morning and I took a picture of the ground, and here's the pinhole effect going through the leaves and the trees. But you're just used to seeing that every day and you don't notice it. But there's an image of the sun caused by light sweeping through the trees. And here's a little piece of foil I poked some holes in and I just made the suns. But if there was an eclipse, you could see the nice curvature. And if you do this real carefully with a good pinhole camera, you can see sunspots on the surface of the sun and things like that. The very last instant before the photosphere is blocked is called the diamond ring. So that's something to look for just at the very beginning of the eclipse, or beginning of the second contact and a third contact, when it just gets blocked and then when it just comes out the other side. This is where you block the photosphere and this is Bailey's beads. So what's happening here is just as the sun is going behind the moon is not a perfect spherical surface. The moon has mountains and valleys. So the light's squeaking between the valleys and it causes these bright spots just before it gets completely covered. That's what Bailey's beads are. And here's where you block the photosphere and you start seeing these red pieces around the sun. That's the chromosphere outside the photosphere, and that's where you might see solar flares and prominences. And then the crown glory is the corona. And the corona, some of the pictures are amazing, but seeing it with your own eyes, and by the way, as soon as the sun is completely blocked, take off your glasses. You don't need any glasses. You can stare right at this. You can't hurt your eyes. As long as the photosphere is being blocked, you can stare right at this. So for 2.5 minutes, or 2 minutes and 40 seconds, you can look at this corona and it's just beautiful. Another image.
So during full, when
it's completely covered, when the photosphere is completely covered, so after second contact and before third contact,
okay.
when the surface of the sun is completely blocked. And I mean, you'll know it, especially if you're wearing glasses, because as soon as it's blocked, you won't see anything. It'll just go black because the filters are so strong that all you can see is the photosphere. And then
Okay.
some people take them off a second early just because it takes a second or two to start hurting your eye, but I wouldn't do that. Let's see. Oh, and this is another picture of the corona that Beth took when we were out on the sailboat crossing the ocean.
Wow.
And you can see it's actually darker than it looks in this picture, but you can see how bright this guy's cell phone is. One of the astronomers that was on this sailing trip, he took this video. So a couple things to watch for. We were very lucky, by the way, to look at the cloud.
Oh, wow.
Yeah. So the captain of the ship and the astronomers were all racing left and right, trying to get us in a position at the exact second, so that we could see. So we're facing east, and the shadow's going to race from the west. So the shadow's going to race this way across the sky. And then it's neat because we have the clouds, because you can see the shadow going across these clouds. And after the eclipse is over, you can even see it go down to the horizon. You can see the shadow go down over the horizon. So now it's total now. You can see the clouds darken. It goes further and further as the shadow goes across the earth.
What part of the world were you in when you shot these things?
We were between the Canary Islands and Barbados. So we were how far out of the Canary Islands? About 2 days out of the Canary Islands on a slow boat.
It's amazing it was that calm.
Oh, we had good weather except for one day. We had one rough day. A lot of broken glasses. Let's see. This is a neat program you can download for free. It's called Stellarium.
Oh, yeah.
So it's like your home planetarium. And it does a lot of things like Google. You can move it around. So we're looking south right now. You can put yourself anywhere in the world. We're in southern Illinois. About several days before the eclipse, but you look around here to the west, and you can look to the south, and you can zoom in and out. So here's the moon. And as I said, the sun's going to travel across the sky faster than the moon. The moon lags. So I'm looking south, so the sun's moving to this way. And as I go through the days, I'm going to go exactly 1 day, so the sun is not going to move, and the moon is going to approach the sun, if I remember how to do this. So there's 1 day, 2 days, 3 days. So you can see it's moving about 12 degrees a day or so. Now, the sun is actually moving too, but it's moving up and down. The sun's moving down because we're past the summer solstice, and the sun's going further and further south. So here's the day before the eclipse. And we'll speed time up. And we go into night. And here's the Milky Way crossing the sky. And all the stars. And here's the day of the eclipse. Oops. Slow down a little bit. So the sky is just starting to darken. Venus is coming out. What time is it here? It's 14. Jupiter's coming out. And there's Total.
Wow.
So it's a pretty cool program. Now they show all these stars. You're not going to be able to see all these stars, but you will be able to see Venus. You might be able to see, I think this is Regulus, right next to the sun. Procyon, Jupiter. But you won't see these little stars. And the closer the stars get to the horizon, the less likely you will be to see them, because it's sort of like twilight all the way around the horizon. That's pretty cool program, though. And how does this apply to hams? Well, so as we talked about, the sun, and Dave showed me this article, the sun is what ionizes the lower levels of the atmosphere, the ionosphere, to allow us to do our HF communications, right? So when the sun gets blocked, what happens? How quickly does this ionized layer go away? What layers are affected? There's multiple layers of ionization. The upper layers of ionization are not only ionized by the sun, they're ionized by cosmic rays as well, so maybe that layer doesn't change. Maybe only the lower layers change. So they're going to do an experiment. If you get on the hamsci.com, you can participate in the experiment by, I'm sure, making contacts, and they're going to record all the data and try to figure out what layers get affected, to what extent, and for how long do these layers get affected by the solar eclipse effect. So I got one more thing. This is another motivator. I have to read this because I can't remember it. But this is just to give you an idea of what it's like to see a solar eclipse for the first time. This was this is an eclipse chaser in 2001. He was in Zimbabwe, and he had all his cameras set up, and he had his video camera running over here, and he had his still camera running. He was taking pictures, and he took all this stuff home, and he's watching. This is a true story. He's looking at his video camera, and he realizes he picked up the audio of the guy that was standing next to his camera, an Eclipse virgin that had never seen one before. So this is what the guy said. This is what he recorded on his camera. And I won't get the emotion right, but he says, "Oh my God, I can't stand it. Look at that. Bloody hell. Oh my Lord. Oh my God, that is staggering. I'm blessed to be alive. My Lord, that is fantastic. My heart is going like clappers. That is like the slowest sex you can imagine. Hubba, hubba, hubba." So you really have to go see this. It's really amazing. That's all I got. Any questions? Yeah.
Yeah, I used to be in EME Moonbounce many years
Okay.
ago. Had a lot of fun with it. And very boring.
Not too many people to talk to.
How does, I never experienced a solar eclipse while I was playing with that stuff. How does a solar eclipse affect?
I would guess you would have a lot of noise. I think you would have a noise problem. It sounds sort of like when, like if anybody has DirecTV, have you ever had an outage because the sun went behind the satellite?
Mhm.
It might be something like that kind of an effect, I would think. Because you're going to have all this, all frequencies coming right at your low noise amplifier. That's interesting though, yeah.
Yeah, I'd never experienced one while playing with that, and I was just kind of curious what it would do. Did it increase communications or just ruin it?
My guess, meaning it would ruin it.
The sun's.
Yeah.
So I'm been trying to figure out what to do during that period of time. I'm gonna be in the total part somewhere.
Okay, great.
For photography, what focal length lens?
Well, okay, my recommendation is don't take pictures. Experience it. I mean, you might take a quick picture or something, but don't spend a lot of time trying to get cameras set up and tripods set up, because all of a sudden it'll be over. And you'll go,
Right. Could you do that
There were people on the ship that were using their iPhones.
Okay.
Sure.
We had just a plain camera. I mean, nothing really expensive. And then there were astronomers that had all the latest
Right.
setup you could imagine.
And this,
Right.
And the neat thing is what you do is enjoy it, and you might, try to take a picture, but then you can go and look at all the pros pictures on site.
Right. Yeah, that makes sense.
and
Let somebody else do it.
it's sort of like,
Good idea. Very good points.
so I used to take a few little astronomy pictures, and said, now I look at Hubble pictures and I go, why am I doing this? It's really stupid.
Very good point. Thank you.
But really, you'll see, during the eclipse, you're looking at the eclipse and you're saying, oh, this is amazing, but stop and look around, see what's happening around you and everything. It's,
Oh, that's good advice.
yeah.
Okay.
All right, thanks.
Excellent.
All right.
Thank you very much.